class will be kind of a continuity from what we did last time, where we looked at the choice of materials. And not only this homework, but the other homeworks that you will have in the future also are part of the learning experience. So it's not something that is already taught and you are trying to just give it out from your memory. It's more of developing from whatever has been done already in the class and getting more information from elsewhere and assimilating it in the sense of the question that is being asked. So that is how it will be. So today's class will be looking at certain criteria to select not the material, which is what that homework was about, but to select the topics that we are going to be discussing over here, because there are so many different potential topics within the ambit of light vehicle structures, and in a one semester course we cannot cover all of them. And keeping the varied audience in mind, many of you are not going to be specializing in structures, I assume, because it's always an equal spread between the four disciplines. How many of you already have an inkling towards structures? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Okay. So that's typically around the number that we have. One of the lucky things I've had is whenever I've had this count, I've seen that eventually at least one or two more get into structures eventually in terms of their project and things like that. So let's hope that happens for the case of structures, but it's important that the distribution is kind of equal for the other groups as well, because each one of them is equally important. So we will look at some of the important topics that we will touch upon in this course, and that will include the fundamentals, of course, which we'll go into in a little more detail, but also certain topics which are generally considered to be more advanced topics or topics only for people specializing in structures. But the way the aerospace field has progressed, the industry in particular, is that everybody needs to know something or the other. So you could be deep in a particular field. It's like a tree. You have a deep roots, but you should have a broad vision. So the whole idea is that unless and until you have that broad vision, you don't know what you're taking your resources for. So you go deep in whichever field you are specializing, but to be aware of what you eventually apply it for, that really helps. So we'll look at those criteria, why we select a few of the topics that we will cover. And this is not only just for the course, but even your textbook goes along the similar lines, because the textbook itself is based on a course that C.T. Sun taught at Purdue, very similar to this particular course. Towards the end of today's class, we'll look at a few ways in which we can classify different aspects of flight vehicle structures, how we can subdivide it and look at it in different forms. And there's not a single basis for it, but many bases for that, and that's what we will try to look at. Okay, so we will start with the fundamentals, and which is what most of the course will be focused on. And we'll have a few words or abbreviations starting with F. So the F words, as we call it. So, but not four-letter words. Many of these are three-letter acronyms actually. So to start with, the fundas or fundamentals involve the materials, and we've been spending some time talking about it in a qualitative sense. We will list out the various alloys specifically, because when we say aluminum alloys, there are so many different kinds of aluminum alloys, so many different series, etc. You must be familiar, some of you must be familiar with steel alloys, the kind of differences they have. Similarly, the titanium alloys and also the composites that we are going to be talking about. All of these have certain different properties and things like that. So we'll focus on the various differences between them, not only in terms of composite versus metals, but within each one of those categories, what they are. Then we will talk about the theory of elasticity. Again, that's a course by itself, solid mechanics or theory of elasticity. There's a lot of mathematical detail which goes into it. We will not cover all of that, but we will see how, to the extent that we can give a flavor of that elasticity, and that is becoming more and more important today. though elasticity or the subject of elasticity has been around for a very long period of time, in terms of its utility today, it's much more significant because instead of the simpler textbook-like structural theories like the Euler-Bernoulli beam theory, or let's say for torsion, you have the Saint Venant's torsion theory and things like that, which were all very highly simplified models. The elasticity theory takes into account all of these simultaneously, and as I was hinting at in the very first discussion that we had class in the other wing of the building, this is very, very critical that we understand why these composites are being used, the difference between composites and metals, and the theory of elasticity is something that will help us instead of using superposition as an afterthought, where it is not applicable because many of these theories are non-linear. How do you bring it up front from the root level, which is essentially means that you consider all potential stress possibilities, potential strain possibilities that are there. So instead of treating stress or strain as scalar quantities, we treat them the way they are mathematically, which is tensorial, without going into the details of the tensorial mathematics, which we do in the other course, nonlinear mechanics of composite structures, where we go in depth into the tensorial mathematics. Here we try to keep it simple, more like matrices that we deal with for stresses, strains, etc., and the relationship between them, how to bring that about. Then in terms of failure, again, there are two types of failure we're talking about. One is the material failure, the other is the geometric failure. The geometric failure I'll consider in one of the F's later on, but right now what we are talking about is in terms of the material failure. And I think in response to one of the questions we had last time, I talked about brittle and the ductile materials, the kind of failures, and how you look at the various criteria that exist for them, and we'll take a look at that. Then as we have been discussing quite often, most of these structures in flight vehicles, the components are either having one dimension very large, which we call as beams, or one dimension very small, which we are calling as thin shells. And in general, for larger aircraft and for faster aircraft in particular, or combination of both, we would have both of these almost equally present in terms of their significance, in terms of load bearing, and in primary structures. So we will look at that. In fact, we will address that question in a little more detail, because that is what is one of the primary differences apart from materials in for flight vehicle structures as composed to any other structures. And as I said, we will look at all of these combined loads, extension, shear, torsion, and bending in both directions, etc. And we will see how the different beams and shells respond to that. So this is what is the major content of the course, what we call as the fundamentals of flight vehicle structures. But as we go through it, we will give a flavor of the 5 F's. And the first F that we talk about is what is commonly abbreviated as FRP, or fiber reinforced plastics, but I'd like to call it more generally as fiber reinforced composites, or matrices, because it's not necessary that you always have plastic as the matrix, though that is the most dominant type of composites which are typically used in aerospace. The reason being that many of these primary structural applications are at temperatures which are not very high, except when you go close to the engine or certain specific other applications in terms of where this flight vehicle is going to operate, maybe in an interplanetary or a different planetary system, atmosphere, or something like that. Then probably certain thought needs to be given into the other aspects as well. But nonetheless, for a lot of aerospace applications where the high temperature requirements are there, we are moving away from thermosets and thermoplastics to metal matrix composites and ceramic matrix composites, and also carbon matrix composites, where not only the fiber but even the matrix is carbon. Essentially what you're doing it in this gradation, you're actually looking at, in the order in which I stated these material names or the matrix names, you are trying to go for higher and higher temperature capabilities. That's essentially what you're trying to do. But whatever it is, there have been options of doing the same thing using isotropic materials, conventional materials, in particular metals. And in the recent kind of structures, we haven't had a large aircraft program for more than 15 years now. This is what currently is kind of almost the state of the art as far as large passenger aircraft are concerned. But there are lots of other flight programs which are coming up in terms of drones and some fighter programs around the world, etc., and also space applications and missiles, etc. But if you look at it, even 15 years back, almost 50% by weight of both these aircraft were composites. And because composites have a lower density in terms of volume, if you actually look at it, it's actually much more. What we are talking about is take all the primary structural components, whatever materials they are made of, and you're looking at what percentage of that volume is composite compared to the overall structural component volume, and that's approximately 70%, and by weight it's 50%. This is what is more important because that's what leads to your weight savings. And in these two cases, approximately 35% structural weight has been saved. Now, what percentage of the structure of the overall aircraft weight is the structural weight will change depending upon the kind of mission and other things. We will cover that in as part of one of the topics later on, so I'll not go into the details of that right now. But for this category of aircraft, wide-bodied aircraft that you have, passenger aircraft, large passenger aircraft, long overhaul, you typically have almost 35% structural weight saving, and that is humongous. It's really huge. It's a great advantage, and it's one of the big things that has happened in the aerospace industry. If you look at the short history that we have had of about 120 years, what has happened in terms of major milestones. One was, for example, the introduction of jet engines. Something similar to that is the role of composites, and that's why it's so very critical. Then, so it's of course the reason why we need to look at it from the user's point of view is that the weight advantage is there, which in turn means the performance advantages that we've been discussing in the previous classes. But from a point of view of a structural engineer, what is so different? You're just using one material instead of other. Yes, for the flight vehicle, it is going to be a great advantage. But in terms of my design philosophy, the design paradigm, how I approach the analysis, is there going to be any major difference? And yes, there is, because these are substantially different, the way they behave, the material behavior that we are talking about, from the traditional materials that we use, in particular metals or metallic alloys. And therefore, then introduction becomes imperative to this material. And the primary reasons why they're different, we touched upon it earlier too, is the heterogeneity, that is, you are having more than one material. Of course, in alloys also you have more than one material. So what's it that makes it so different in the case of a composite? Anybody?
Metal, it's a alloy, means it is a uniformly mixed and having a properties same in all the directions. But in composites, directions are different. Means strengths are different in different directions, and materials are not mixed in a homogeneous fashion.
Okay. Okay.
And in a composites, basically the load carrying fibers or that particular will be in some orientation where the loads are active. But in case of metal, it is not like that. And that is one. Other than this, this aesthetic point of view, I can say like that metals are better as compared to composites.
Okay. Okay. Anything else? Anybody?
Joining, when it comes to joining techniques and stuff.
Yeah.
Metal can be welded, but I presume composite has to be used with fasteners or distinct joining techniques.
Right.
And also, I think composite, especially the thickness direction, the strength is not as high because that is a problem again.
So that's an important point you mentioned. From a more mathematical perspective, we call that as isotropic and anisotropic, right? So tropic means direction, iso means same, and an is a negativity for that. So anisotropic basically means it's different in different directions. The properties you talked about, the thickness direction, for example. So the reason why it is different, so these two categories are different, that metals from the composites, is the fact that one is the heterogeneity and the other is the anisotropy that you have, both of you have brought about in various different forms in terms of how it expresses itself. But the question I'm asking is that the reason for the heterogeneity or anisotropy in a composite, FRP in particular, is the fact that you are having more than one material. You're having a fiber and you're having a matrix. So whereas in an alloy also, typically you have a fairly large number of metals which are coming in. So it's also a mixture. In a sense, from a layman's perspective, both are mixtures. So what is the difference between one mixture, which is the alloy, and the other mixture, which is the composite, which makes the composite a little more difficult animal to deal with as far as the engineers or analysts or modelers are concerned. What is it, why is it that the mathematics becomes a little more complex for composites compared to alloys, even though both are mixtures? What kind of difference in the mixing is there? Or
The homogeneity.
uh-huh.
Homogeneity in the alloys, that is in a greater extent. For if I talk about an example, a nickel steel, where if we look at a bar of nickel steel, we don't have 30% nickel bar this place and 30% we mix it completely.
Right.
There is a greater amount of homogeneity in that mixture compared to the composites, where it's visibly clear that if you talk about this ply, there is visibly clear that different layers are there. So if we, in sort of workability, or in sort of other things like load bearing things, so the deviation of the property, material properties, if we go along the direction of the joining of different composites, that will vary greatly compared to the alloy, because there is a more homogeneous mixture is there.
So I think you brought it out in quite a clear manner. But essentially what is happening is in terms of the length scales that are involved in a mixture. So one case, the length scales that are involved, as you said, it's visibly discernible, which means that the length scales involved in an FRP are much larger compared to the length scales that are involved in an alloy, which is what makes it almost homogeneous for all practical purposes, that the length scales that we are interested in. From a material science perspective, somebody is modeling from a material science perspective, they might go for lower, even lower length scales and actually look at the differences in terms of the crystal structures that are involved and what is actually happening across the interface boundaries of these different alloying elements and things like that. So, and also the reason this is very important is that can you think of, see, I already mentioned that one of the complexities of an FRP is the fact that it is anisotropic, that is, properties are different in different directions. But is it possible for alloys, any particular alloy or category or class of alloys to have anisotropy as well? The one thing is the lower length scales at which the homogenization is done. The other thing is in terms of the distribution, usually it's a little more random compared to what we have in an FRP in terms of how we have it. So that is one thing. But in spite of that, is it possible to have a class of alloys where there could be anisotropy? Okay. Okay, just a minute. Yeah, finish it.
The grain length will be different. So
Right.
Yeah.
Yeah, very good. Yeah. You were mentioning
Adding
something.
impurity basically is
Right.
some
Sure.
form of either treating mechanically or adding some component which is localized in one particular.
Yeah, so essentially certain production processes is what you're both talking about in terms of what could probably create and sometimes an undesired heterogeneity and or anisotropy, and sometimes a desired one, as you were talking about. Another example of a desired way of creating this anisotropy is in aerospace applications is especially for turbine blades. See, compared to compressor blades, which experience very low temperatures because there is incoming air, it's almost the ambient temperature that you have at whatever height the aircraft might be flying at. The turbine is experiencing the burnt up air which is combined in the combustion chamber with the fuel, and therefore it's at a very, very high temperature. So some of the alloys which are used for turbine blades are what are known as single crystal materials. So like, for example, nickel is used for that to a large extent. So there you would see that because of the way the crystalline structure is developed and how the blade itself is actually manufactured, so the kind of manufacturing techniques you described, that creates certain grain boundaries in desired directions, probably along the length of the beam. If we think of the turbine blade as a beam, it's a short beam, short stubby beam, it's very highly twisted, but essentially it is a long structure, shell-like structure, you can model it as, or as a beam. In either case, there are certain directions in which you know that the loads will be dominant. In other words, for example, because it's rotating at such a high speed, there will be centrifugal forces, which means the axial load. So you would want the crystalline geometry to be such that the maximum properties that you're having is in this particular direction or along the length of the blade. So that is something that is kind of worked in through the manufacturing process. Though alloys by themselves do not have that, as you explained before, we try to build it in, if possible, in certain very niche applications like these. So we will come into the mathematics of that a little later. This is just, we're still talking about it in a qualitative sense. The first F we have covered out of the 5 Fs, which is the FRP. The second F we will go to is the fracture mechanics. The fracture mechanics again is a course by itself. In fact, there are courses in our own institute, especially in other departments, civil as well as mechanical, on fracture mechanics. There are also a lot of fracture mechanics related research that some of my colleagues do in this department as well. And so it's a very, very complex subject if you go into the depths of today's state of the art. But there are certain very basic aspects to it also. If you just understand those, it will really help you even if you're not a structural engineer. And why it is so important is the fact that we talked of two different kind of design paradigms, fail-safe and damage-tolerant kind of a design. So the fail-safe we talked about in terms of redundancy. So for example, structures like the landing gear and or the attachment point of the wing to the fuselage or the stabilizers to the fuselage, you will typically have some redundancy so that even if one component fails and some other component will take care of. A non-structural example of redundancy is, for example, in passenger aircrafts, the engines. So whereas in fighter aircraft or many military aircraft, you are allowed to have a single engine aircraft. For passenger aircraft, you typically have multiple engines, 2 or 4 or 6, etc. And the reason is that even if one of them fails, by an appropriate deflection of the control surface, in particular the rudder and the aileron, the pilot should be able to, with a larger amount of fuel consumption because of the larger drag that is involved, be able to safely land at the nearest airport, if not the actual destination that they were supposed to go to. So that has always been too much of backpack weight in terms of the aircraft design philosophy. So people have been trying to get rid of that from many components for which it was applicable in the past from a structural point of view to as few as possible. And as one of the new paradigms, new in a relative sense, because this has been around again for decades, is damage tolerance. And to be damage tolerant means that even if a certain level of damage has occurred, of course the damage has to be defined in a particular way in terms of its severity, etc. So for less severe kinds of damages, even with the damage, can you still fly the aircraft and eventually have certain operations performed on it to rectify that issue, whatever was occurring. And that is something that has caught on to enhance the efficiency of aircraft over a long period of time. And especially when you're applying that damage tolerance design for composite structures, it's true for metallic structures also, because most of the body of knowledge as far as fracture mechanics is concerned has come from metal fracture mechanics. And the fracture mechanics of composites slightly different because they are brittle, and brittle fracture is quite different from how ductile materials fracture. But nonetheless, some of the terminology and concepts and other things are same, just that their mathematical variations with respect to the field variables are quite different. So whether you are talking about composites or the aluminum alloys, titanium alloys, etc., fracture mechanics becomes almost an tool that is kind of unavoidable for most design teams, as well as analysis, especially when you're doing accident investigation and things like that where structural damage is involved. So you will see that the fracture mechanics plays a very, very critical role in understanding where the faults could be and how improvements could be made in terms of avoiding such incidents in the future. And this is important not only for older aircraft, where of course the fracture is an actual practical concern almost on a day-to-day basis, perhaps in many situations. So what we call as aging flight vehicle structures. But for newer designs, we are taking that up from the preliminary design stage itself in what is known as a non-deterministic design. So for a lot of the theory that you have, whether it is in structures or any other field, for a long period of time, the way bodies of knowledge have developed is in terms of a deterministic sense. Deterministic, the word comes from determine, that is, you're able to determine something. So you have a certain level of confidence in the knowledge that you have, especially of the data for the materials, the data for the flight conditions, let's say in terms of the atmosphere. For example, you might be studying the international standard atmosphere in your flight and space mechanics. So these things are certain models that we have, and there could be a variation from that. For example, there could be a gust, etc., which could change a lot of the properties of the pressure, temperature, or density you have at a particular altitude because of the various currents that might be ongoing at a particular point of time, or various interplanetary or lunar effects and things like that. So keeping that aside, one is in terms of the environment, that is the ecosystem in which the flight vehicle is. The other is in terms of the flight vehicle's material components itself, that is the materials. We're going to be having not very clearly specified values of many properties. The properties can change and change over time. And even at a given point of time, even if you have sourced the material, let's say from a same manufacturer in the same lot, you make specimens from one end of the lot and another end of the lot, you are going to have some scatter there. Of course, with the kind of material processing technologies, this is reducing over a period of time for the same material. For newer and newer materials, the challenge still remains. But nonetheless, there is going to be a scatter, and if you do a fairly large number of tests, you will find that you will typically have a probability density distribution function rather than a specific property. Remember that when we talked about the weight savings, we talked about two specific parameters, the specific strength and the specific stiffness. That is sigma u by rho and E by rho, where rho is the density, sigma u being the ultimate tensile strength and E being the Young's modulus. But that was assuming that these were all specific values for a particular material. But you could have a scatter and you could actually have a PDF, and which means that sigma u could have a PDF, rho could have a PDF, and therefore sigma u by rho could have a different PDF by itself. And when you use these PDFs as the inputs for your material properties in terms of overall design, the even essential things that you're looking at, let's say the aircraft's range, or let's say the aircraft's maximum speed that it can go, that will also be a PDF, and it will not be necessarily a same type or same shape, a Gaussian kind of a thing, because there's so many models that are involved in between these two, from the structural model to the aerodynamic model and the flight mechanics model, and each one of them, if you want to consider it accurately, are all nonlinear, and therefore it's not a trivial extrapolation going from one PDF for, let's say, the Young's modulus eventually to say what kind of deflection will happen in the wing tip. So there's a lot that changes between them. Only thing we know is that final value is also not certain. That's also going to be some kind of a probability distribution, but what kind it is has to go through the model in order to arrive at. So because of all these reasons, non-deterministic designs have caught up, especially in the sense of the factor of safety that we talked about, 1.5. Instead of blindly following that, there's a room that some of the certifying agencies are giving, at least to cases where not too much of life or risk is involved, like for example drones and things like those applications, to go in for lower factors of safety based on certain non-deterministic criteria that you can arrive at, because you have a certain confidence level, not 100%, but you have a certain range that you're talking about in terms of the mean and the standard deviation that you have, and based on that you're able to give a certain level of confidence, and therefore you might arrive at a logic for determining a factor of safety for certain specific cases. So keeping all that in mind, instead of without going into the details, the basic aspects of fracture mechanics one needs to understand, because without that you will not know how to modify these traditional conventional design paradigms. So it's highly desirable for engineers to get an exposure to some of the fracture mechanics concepts, in particular what is known as the strain energy release rate. Rate you typically refer to with respect to time, but here we are talking about with respect to a crack growth, for example, how the strain energy is getting released when a material is getting cracked, and as the crack length is growing, how that strain energy is getting released. Because we are going to introduce elasticity not only from a stress strain perspective of we're not going to tensors, as I already told you, more of a matrix algebra kind of a thing. But similarly, when you're talking about this same thing in a holistic sense, that is combining all of these different kinds of deformation and with anisotropy, etc., put into place, energy methods play a very, very critical role, and therefore a lot of these modeling we'll be discussing in terms of the strain energy, which is essentially the energy by which the material elements store whatever work that you're doing by applying a load onto the structure. There's some deformation that is taking place, because of which some strain is developing, and because of that strain it is storing certain strain energy, which is typically a potential energy. Just like when you lift a ball and have it at a height, you're essentially having a latent energy, which you call as the potential energy, and that can be used to do some work by dropping the ball, for example, so it gets its kinetic energy, etc. So similarly, there's a way in which the latent energy is stored, which we call as the strain energy. We'll go into little more details of that later, but the strain energy release rate is built on that concept. So it will not be very difficult for you to understand that, and especially from what is known as the Griffiths criterion. We will just touch upon that a little bit later on, and that is built upon the strain energy release rate, and that's how this particular topic will get addressed. Maybe I'm jumping the bandwagon, because later on I'll talk about each of these 5 Fs, how I will probably be dealing with, so then I'll get back into that. So that is the second F. The first was FRP, apart from fundamentals. First was FRP, second was fracture mechanics, and the third that is very essential is fatigue. And many of you, right from the first class, you've been pointing out that one of the primary differences between flight vehicle structures and any civilian or other static structures is the fact that there is motion, there is dynamics, and some of this dynamics exhibits itself in the form of fatigue. there's essentially cyclic loading that you're going to have on various structures. If you look at the overall aircraft itself, it's going through so many cycles in its 30-year lifetime. Every day it's flying from one particular place to another particular place. If it's a short haul, maybe multiple flights in a particular day. And each one of them involves all those phases of taxiing, takeoff, climb, cruise, and descent, landing, and again taxiing. So, and all the maintenance that happens in between. So, all of these create a certain level of fatigue in the overall behavior. And particularly the structural components that are there, especially for example, if you're looking at the wing, you know that the predominant load on that is the lift distribution, because of which it is bending up. So the top surface of the wing, which includes the skin as well as the stringers and the flanges of the spars, etc., those are going to be undergoing a fairly large amount of compression. But each time you come and land, again your lift is going to come down to zero, and eventually it's your the weight of the wing which is going to go pull it down, which means it's going to now be in tension. So what was in compression becomes in tension. So in fact the bottom, it's the other way around, it happens. So essentially at a certain time scale there is some kind of a cyclicity that is happening in the load, and that is what we want to look at. This is a little more larger length time scales that we are looking at. We could have even smaller time scales in terms of the vibrations that are involved, the structural vibrations, etc., which could be at higher frequencies. And so it's a combination of those. And so in other words, it's not like you haven't what is known as an SN diagram, where you plot the maximum stress that the material can take at any given number of cycles that it takes to failure. And you see that at static loading, it has a certain good strength. And as you start increasing these fatigue cycles, you see that it slowly reduces the strength capability of this particular material. But what we are looking at here is not a particular kind of frequency or whatever that it is going through. It is at a fairly distributed, some large frequencies, some small frequencies, different kinds of load magnitudes between them, how you accumulate all of that. So all of that becomes critical in understanding the fatigue, and which in turn reflects in terms of the durability of the aircraft, how long it lasts, or at least of the structural components which you need to replace at a particular regular interval. So many of these maintenance, repair, and overhaul operations are dictated by these fatigue laws. So, and building a certain factor of to avoid the uncertainties and risk that is involved in the modeling, you have built in a certain factor. But essentially this plays a critical role in arriving at the schedules of maintenance, how frequently a particular structural component needs to be inspected, how frequently a particular component needs to be, after inspection, taken to a more involved test, or it has to be replaced or repaired, or maybe the attachments to it, how they have got affected. So all those joints and other things have to be taken care of. All of that is going to be very, very critical. So because of the dynamic loading that is involved. So those are the first three Fs. Let's look at the next one, which is something that is, fetches a lot of people jobs, the FEM. So finite element method and finite element analysis, FEA, as some of us call it, essentially is implemented in the form of lots of commercial codes that are available today, like ANSYS, Abacus, Nastran, etc. And many of these are extensively used by the aerospace industry. Every big or even small aerospace companies, you will see that typically have some of these tools, and they use it almost on a day-to-day basis, whether they're doing a new design or trying to improve the existing designs, or analyzing certain issues that are occurring with their users for the particular aircraft, etc. So finite element method is becoming almost like the way, the means in which many of these are accomplished. In last class when I wrote that 3D is equal to 2D plus 1D, breaking up any structural component into either a shell or a beam, and therefore involving one large length scale, the other is a smaller length scale. That large length scale is what is typically needs to be done by using finite element method if people are intelligent enough. Because what happens is with the kind of improvements that we are having in computational power, both hardware and software capabilities, it's become almost routine for some industries to just go and pump it into a 3D finite element analysis for anything and everything. But experience has shown that some of the better performing companies, especially those with the larger R&D part to their organization, typically have a much better way of approaching the problem. They recognize that most of these structures are either shells or beams, and therefore you can do with 2D or 1D models as long as you have a reliable 2D or 1D model. In other words, it should give almost as accurate results as your 3D model, but it will save you, let's say, 10 times or 100 times the computational time. It may not look large for a single run. Instead of 100-second run, I'm doing it in a 1 second. You're saving only 99 seconds, but this is done on a repeated basis, day in and day out, minute after minute, by so many different engineers that all of this accumulates. And it's that what creates a much more efficient algorithm and an efficient code, and therefore its implementation. And that's where that lower length scale that we are talking about, in the case of a beam, the cross-sectional analysis, in the case of a plate or shell, the through the thickness analysis, which can still be done in an analytical closed form without having to resort to finite element method. And therefore, if you do that in an appropriate way, instead of using some very simplistic models that we have learned as part of our undergrad, like the Euler-Bernoulli beam theory, instead of that, if we go to something which is much more rigorous, and therefore based on physics, based on more rigorous mathematics, then the reliability of that cross-sectional analysis of a beam is very high. The reliability of the through the thickness analysis of a plate or shell is so high that you can avoid 3D finite elements to the extent possible. There are certain regions where in spite of having a very good cross-sectional analysis or a through the thickness analysis, you can still have the beam and shell theories on the one hand, what are called as dimensionally reduced theories, performing very inferior compared to the 3D finite element. And one such example is the joints. For example, where the wing is joined to the fuselage, you have fairly complex structure. So one is the geometry can be complex, the material distributions can be complex. In such situations, your dimensionally reduced order models will fail. But you still, for the majority of that same wing, you could still be using a 1D model or a 2D model. But when you come close to this, if you want to get accurate stresses, accurate deformations, you need to go for a 3D finite element analysis. So one is because of the complexity of the material that is involved, complexity of the geometry that is involved in the joint. But the third thing is something which is basically coming from physics. Many of you from your strength of materials might be familiar with what is known as the Saint Venant's effect. So it's essentially an end effect. So when you go close to an end of the structure, the way it actually is, the boundary condition is, will matter. So in other words, the resultance is what matters when you go farther away from the boundary. When you go closer and closer to the boundary, the actual distribution of the contacts that are there over there, the contact mechanics and the joint mechanics, all that starts playing a very critical role. And that's why you need to go for finite element. So the whole idea is some level of judiciousness is involved instead of blindly applying the commercial course. Yes. Very good. Yeah, it's an excellent example that you brought out. It's something because most of the aerospace structures, we're going to use thin structures, whether it's a shell-like structure or even the beams are going to be thin-walled cross-sections. It could be either thin-walled open cross-sections like IET, etc., or it could be the closed cross-sections. It could be circular or box beams and things like that. All of these are going to have thin structures, and the way they are loaded is also such that it's almost approximately a plane stress condition. So a plane stress approximation might do good in most situations, but it's instead of assuming that, if you can let the mathematics do the job for you and say, yes, this is a right case for applying plane stress, this is not a right case for applying plane stress, because sometimes just these thumb rules that you have, that if it is so thin and if it is the load is of certain type and the boundary conditions are a certain type, it will always be plane stress. There could be exceptions to that rule, and the other way around too, where you might think plane stress is not applicable, but it might be applicable. So let the physics and the math do the job for you, because unlike 100 years ago, or even let's say 20, 30 years ago, the kind of physics and math we had to understand these concepts, very different from what we have today. So there's a lot of development that has taken place. We have much more level of confidence there. So use that and let that decide. But that is a very, very common example that you brought out there about plane stress, plane strain, and when to use and where to use. And especially for aerospace applications, that becomes very critical. So planes, in a plane stress kind of a situation, what you would have is that the through the thickness stresses are assumed to be zero, but in reality what actually happens is that the through the thickness stresses, if it, let's take a plate like this, along the length, if I draw coordinate x1, along the width I draw x2, along the thickness I draw x3, then what you're saying is that the stress is sigma I3, that is all the stresses on the third phase, which is a normal stress like this, a shear stress like this, sigma 2, 3, and a shear stress like this, sigma 1, 3, are all very, very small or negligible, infinitesimal compared to the other stresses, which is sigma 2, 2 in this direction, which is pulling or pushing here, sigma 1, 1 in this direction, and a shear sigma 1, 2 that is there. So sigma 1, 1, sigma 2, 2, and sigma 1, 2 are very large compared to, in general, compared to your other three stresses, sigma, which we can call as I3, where I takes on values 1, 2, 3. Now, if you are using that concept, and if it is true, then delamination will never occur. In a composite, delamination is something that between two layers, because there, as I said, there are more than 80, 100 layers in a typical skin construction, similar in the case of many of these stiffening structures also. So many of these fail by different ways. It could be a fiber breakage, it could be a matrix cracking, it could be a fiber matrix debonding that is happening. But one of the most common things that occurs is two layers separating from each other, either at the edge, what we call as an edge delamination, or somewhere in between, which is even more dangerous. You may not even be able to observe it in visual inspection or many other inspection techniques, and that is essentially an internal delamination that is occurring. Now, if at all these delaminations were to occur, these stresses have to be there, the sigma I3. In other words, there has to be either a peel stress, that is a normal stress which is pulling these two apart, or there has to be a shear stress which is pulling these apart, and it is so large that it's more than the interfacial laminar strength that you have, interlaminar strength. So the interlaminar shear strength in this direction could be lower than the stress that is happening, or combination of these, in which case it could happen at a much lower stress values than you expect. So this will not be captured in a plane stress kind of an approximation. So a plane stress would have given you the advantage of using a 2D model for this. It would simplify it so much that you might be able to do the same problem 10 times faster, let's say, in terms of your CPU time that you take for running the same code. But because you're putting sigma I3 equal to 0, you are not able to capture that. But there are workarounds for that. One workaround would be to go back to what is known as your 3D equilibrium equations, because the 3D equilibrium equations still have your sigma I3. Now, from a plane stress approximation, you have found out sigma 2, 2, you have found out sigma 1, 1, you have found out sigma 1, 2. You use these three as knowns now, their distribution, how they vary with x and y and z. Now, Of course, they don't vary with Z because it's a reference surface that we're talking about. Now using that, you can get the sigma I3 values. Yes, they will indeed turn out to be, if it's a really thin structure and the kind of loading is such, then and the boundary conditions are in a particular way, you will indeed get a plane stress. So in other words, sigma I3 will be small, even when you calculate it from the equilibrium equation, but it will not be zero. It will be a certain value, and that value can have a huge impact on your overall design in terms of avoiding delaminations and things like that. So that's so that judiciousness is what we are talking about over here, because the kind of the same course when I took it, probably 30, at the risk of telling my age, so probably 35 years ago, as a bachelor in IIT Madras, or even here, I did my master's here, similar to you, but that time it was called an ME instead of an MTech. That was 30 years ago. And the kind of thing that we used to do was solve problem after problem after problem, especially thin-walled beams, torsion, flexure, shear, go on solving problems, and the exams and assignments were all like that. But yes, that is still important, but not to the extent that we used to do it at that point of time, because a lot of those, of course, are based on simplistic theories which are not of much practical relevance in the industry anymore. It gives you some kind of an insight into the problem. So to understand the theory, those simplified theories, and just apply it to some one or two examples is good. In terms of understanding the overall behavior, but then you have to slowly move over to what is actually used in the industry and that's the reason why people who are doing FEM courses are getting better jobs compared to those who don't, of keeping other things the same. So one is, we want to shift that emphasis from that problem solving drill to have some kind of an ability that you develop in each one of you in terms of how you understand the mechanics of the whole thing. And finite elements is something that is essentially a discretization that is happening, a numerical discretization, and that need not be applied only to structural problems. It could be for many other problems also. But essentially what you're trying to do is to understand the overall physics or overall chemistry, overall science that is happening in that problem domain that you're actually working on. And once you do that, that is one goal of this whole way of introducing FEM as part of a flight and flight vehicle structures course, is that to understand the mechanics in a better way. The second thing is that, because the reason why you understand mechanics better in the way in which it is introduced is that we will be removing some of the assumptions and approximations that we have been typically doing, saying why they are not required. One is either because they are not applicable for that particular structure, the way it is loaded and the way it behaves. The other could also be because you want to go for more and more complexity that you want to deal with. Earlier days, it was unthinkable to deal an entire aircraft wing finite element analysis, but today it's done almost on a routine basis by many companies. So that is, and unless and until you understand what is the mechanics behind it, the model is so complex that if you make even a small mistake in the data entry or in interpretation of your results, that's going to cause a havoc. So it's very important that you understand what is the physics that is happening behind it, and also the way you formulate the problems. Many a times it's the way you formulate the problem is half the solution done, because if you formulate it in the way in which we gate setters or some other competitive exam setters set the question, obviously you're working against yourself, because we unnecessarily try to twist the question and try to get your understanding rather than from memory through your way of logic and how you work out. It's a different purpose for which it is done. But here, on a routine basis, when you're using it in the industry or even in an R&D lab, etc., you want to formulate the problem as straightforward way as possible, so that you're not already the whole thing is so complex. Why you want to add complexity in terms of the way you formulate? And there's no one right way or wrong way of formulating the problem. There are many ways of doing it, and some of them are equally efficient. So just that certain people are used to particular way of formulating the problem. So how you state that problem is very important, and this is the reason why I probably dedicate one full class to understanding the different variables that are involved with structural mechanics, solid mechanics, elasticity, etc., and in particular applied to flight vehicle structures, and see what is the position of each one of them. It's to go beyond or behind the scenes from just the names that are involved, all the slang that we use in the industry or the ecosystem, to go behind that and see from a basic physics or maths perspective, what is it? And then you would see that there's a much more straightforward way of formulating the problem, and that helps you to have a much more efficient way of arriving at its solution. The third thing is, of course, in most cases, because of the robustness of these commercial codes and the number of years that they have been in service, tested by not only the FE code providers, but also the users, and the feedback that has been given to them, and the improvisations that has been done, the additional subroutines that have been added to make it much more robust, etc. You'll always get results, but whether that result is correct or not, to gauge, and how you utilize that result, how you put that result into actual practice in terms of improving the design, or let's say for the future aircraft to take some, have some takeaways for that and things like that. So all of that will depend upon your ability to judge the correctness of the result, and to probe further in terms of the post-processing to see how you can utilize whatever you have to arrive at certain things which may not be trivial. Just by looking at the results, you may not be able to get that, but by a little bit of post-processing of that, you will be able to arrive at certain certain qualitative or even quantitative results, which might be very critical in your overall decision making, not only for your team, but for probably the entire company. So that's what we will look at. And the essential thing is, we will look at a few simplified ad hoc techniques and show their limitations, and show also how the FE can probably avoid that. So there are separate FE courses that are some which are rarely offered in this department, but almost on a regular basis it's offered in the mechanical and the civil engineering and a few other departments. So some of you specializing in structures probably would take that, and some of you already probably have experience working on the FE codes. But so we will not go into the actual coding and the and all those things. It's more from the point of view of how the theory behind it is, and how it can be actually applied in a qualitative sense. So we will not go into the nitty-gritties of it. So then the fifth F that I was talking about is flutter and related instabilities. Flutter is a dynamic aeroelastic instability. Similarly, you could have static aeroelastic instabilities like airfoil divergence. You could also have elastic instabilities which do not involve the aerodynamic forces, which is essentially buckling that you have already looked at. There's something called local buckling, apart from the global buckling that you're all familiar with, the wrinkling and a few other small differences, but essentially they're all instability problems. And in all of these, we are of course assuming the material to be elastic. That's why we call it elastic buckling or aeroelastic buckling. By elastic, of course, we mean that there's no remnant strain that remains after the unloading. So in other words, in a mathematical perspective, you're saying that the stress is a function only of the strain. It's not a function of anything else. Whereas if it's a function of something else, like let's say the strain rate or the history of behind what loading and unloading patterns that component went through earlier on, and therefore how that material behaves, then you're essentially going into inelastic regimes like plastic or elastoplastic and a few other more complex things. And for most practical purposes, if you look at the way the aircraft structural designers have designed these structural components, very rarely many of these material components get into beyond the elastic limit, and therefore elastic models are good enough. But when you're talking about failure and you're essentially looking at the validity of your factors of safety, or you're looking at an accident investigation, the structural damage that has occurred, etc., or for research when you're looking at damage mechanics, or you're looking at new material development where you're trying to understand the damage mechanics of that, all of those cases you cannot live with just elastic theories alone. You have to be able to go beyond that. But this course will be limited to elastic models. Though we will go beyond isotropy to anisotropy because we are considering FRPs, and beyond homogeneity to heterogeneity because we are considering FRPs again. So coming to the last F here, the flutter, buckling and other elastic or aeroelastic instabilities, they have a strong influence not only in the detailed design but even in the preliminary design stage itself. I think in passing I mentioned in one of the earlier classes that the wing skins are allowed to buckle. Just a few minutes back we were talking about the lift being the dominant load, and therefore the top surface, especially the top skin, is under compression, and that compression can, because it's a very thin skin, even though it might have 80-100 layers, it's a large aircraft and the loads are so large, and the distances between two adjacent stringers and or spars, which are the reinforcing beam-like members inside, are could be fairly large, and therefore you have a large panel which is thin and subjected to fairly large compressive load, then because it's a bending load which is experienced by the top surface as a compression because of the direction of the bending that is there, and therefore it can undergo buckling, and typically it operates in a post-buckling regime. So in other words, in an actual flight you could probably be having many parts of your upper surface of the wing or even the some parts of the tail which are the skin which are already buckled. So in other words, geometric failure or instability rather has occurred, but no material failure is there, and it will come back to it's still in the elastic limits. So that's why we call it elastic instability. And but nonetheless, these phenomena need to be understood, because once this has buckled, this skin has buckled, the top skin of the wing surface has buckled, you can no longer count on it for taking the load, or at least you cannot count on it to take all of the load. How much of the load that you originally designed it to take, and if it had not buckled, and once it has buckled, and which means that the extra load that is relieved from the skin has to be now be taken by the stringers and the flanges of the spars. So how that realignment takes place, the redistribution of the loads and the way they are transferred, all of this is very important, and it's very interesting. So without going into again the details of it, we will look at from a qualitative perspective that also to see how all of these instabilities, what kind of effect it has. So another example, I was just talking of fixed wing aircraft, but in rotary wing aircraft, again, it's a very commonly used thing that many of these composites have a lot of different couplings, as we were hinting at some examples in the very first class. For example, you might be applying a bending and it is twisting. So there is what is called as a bending twist coupling. So in other words, you apply a torque, it will bend. If you apply a bending moment, it will twist. Of course, it will also bend, but there is a secondary effect that is happening. And in the initial stages when composites were introduced, people were thinking, oh, this is very dangerous, and this can be deleterious to the whole mission. But ingenious people started thinking how to utilize that. So that is the whole idea. When you have something is a stumbling block, you essentially use that to gain better success, right? So essentially this coupling that is there can actually be sometimes utilized in a particular very effective way. And you don't need to have even composites for that. Even with just a metallic aircraft, isotropic materials, you would still, if you had, let's say you had a wash-in or a wash-out, which is essentially from a structural engineer's point of view, a twist that is given in the beam. So now this twist that is there in the beam that can actually induce a certain coupling which was not there in the straight beam. So similarly, your tapers and curvatures that you could have, for example, at the winglet, you could have a small curvature. So that portion, there could be fairly large couplings that are happening, even if that were not made out of composites. So can you actually work around and utilize those couplings to your benefit? And one example is the large rotors with soft material blades that are typically made, because these are having large deformations, so allow for large displacements, large rotations, but still you could have small strains. So you're still within the elastic limit, but the reason why these displacements are large is that the structure itself is large. So in other words, if you have a small aircraft and a small wing that is there, then the displacements and rotations will be small for a given strain. For the same strain, a larger wing or a rotor blade will have much larger tip deflections. So essentially, the strain remains the same, but the displacements change, because the derivative of the displacement with respect to the coordinate systems, whatever coordinate measures you have, is what eventually gives you the strains. And once this dimension is increasing, because it's a real beam, a wing or a rotor blade even more so, then you typically have a situation where you have large displacements and rotations, but you still have small strains. So when you have such a situation, you essentially are dealing with soft blades, and this is common not only in helicopter rotor blades, but even in wind turbine blades. You would have seen we are investing a lot in wind energy in India in the last few years, and Northern Europe, the Scandinavian countries also have been pioneers in that for many decades now, and some of them actually manufacture humongous blades. You would have seen some of these being transported on the highways too, causing a lot of traffic delays and things like that. So these are fairly long structures, and many of these are made out of composites. There's a company called LM Glass Fiber, which is now taken over by GE Renewables. So I teach some composites courses for them, and some of the things that they do so very interesting and great for aerospace engineers to learn. And one of that is essentially this: when you're having such large rotors, you cannot think of such large rotors on an actual flying helicopter, at least in the near future. So what we are talking about is different extremes that people operate in other situations. It would be a ground-based structure, but it is rotating, it's dynamic. But the behavior in terms of the overall dynamics and also the structural dynamics is somewhat similar, and there's a lot of learning that can happen both ways. From helicopters, they can learn, and from wind turbine blades, we can learn for helicopter blades as well. So the advent of large rotors with soft blades means that classical flutter becomes very common. So because the larger the blade you have, you can think of it, because right now you may not be familiar with aeroelastic instabilities, but even if you look at the elastic instability like buckling that many of you are familiar with, for a typical Euler column that you have, pi squared EI by L squared is what you have as the buckling load. EI is the bending stiffness, and L squared is the length of that column. So the larger the length, the more susceptible it is to buckling, and the lesser the stiffness, it is bending stiffness, it is more susceptible to buckling. And bending stiffness again means that if you have a material which is having a lower E, or it's having a geometry that is having a lower I, the cross-sectional moment of inertia, in both these cases, you're going to have more susceptibility to that. So that's essentially what is happening with a soft blade and a large rotor. You are in for such a instability, even from a very simple model that you're familiar with, because pi squared EI by L squared will not be applicable here, because the boundary conditions are different. This is a cantilever almost, because it's almost like fixed, and this is a free end. So you would have to make the appropriate modification. Also, it's not a prismatic beam, it's changing, and it's also twisted, and the composite materials that it is built of, etc. So what we're essentially saying that instead of looking at that as an issue that there is an aeroelastic instability, we can see how to work around and reduce that aeroelastic instability by utilizing some of these couplings that are there, which we thought were probably something that is going to be detrimental. So one way to do that is what is known as aeroelastic tailoring. So you know the flutter equations. So based on the flutter equations, you know what material properties, what geometric features are contributing towards that, how sensitive is the flutter load to each one of these quantities, which of those you have a little more leeway in changing the design values so that you're not affecting the other performance attributes of it and still be able to do it. And one such thing is both composite tailoring as well as aeroelastic tailoring, where we try to bring in a twist and bending coupling, so that once this twist and bending are coupled, this instability can be delayed. Because remember, what we are talking about is a flexural, either a flexural buckling can happen. I think I discussed this earlier, where I said that if the flexural stiffness is very low, when you're applying a compressive load, it could bend and have a instability like that. Or if the twist is, torsional stiffness is very low, then the same compressive load could create a twist. Now you're bringing in this twist and bending coupling, so that you might have neither a flexural buckling nor a torsional buckling, but a flexural torsional coupled buckling that can happen almost simultaneously. So in other words, you can push the limit of what flight conditions under which this can occur to outboard to beyond your VN diagram, or what you call as the flight envelope, so that this is not a thing to be worried about in normal design conditions. So provide that twist bending coupling to shed the wind turbulence load. So because of the turbulence, there are certain wind loads which are coming, whether it is the wind turbine blade or for a helicopter rotor blade, and those are situations in which this can typically occur, the aeroelastic instability like a flutter. Now, instead of that getting initiated, you are seeing how this coupling can shed that energy, because essentially it's all an energy management that you're doing. How you split that energy that is coming from external sources. One is because of the flight, the other is because of the gust, and then how you're trying to distribute that energy instead of going all towards bending, in which case probably a flexural instability would have occurred. You are distributing it between the torsion and the flexure so that neither of them occurs. So that's essentially the intelligence of the design, and therefore overall the end effect, the moral of the story is that the blade's proclivity for flutter comes down. So either you can avoid it or you can delay it to the extent possible. So this is, I think, the 5 Fs. Probably I think I have a little more time to go into one more slide. Yeah. So let's see, are there any questions so far, so that I can address that before going to this? Yeah. So coming to each one of those Fs, let's leave alone the fundamentals, because we'll actually spend a lot of time on it. But each one of these, how we plan to address this, because as I already mentioned while discussing each one of these topics, there is a separate course for each of them. There are separate books for each of them. Each of them is a separate research field by itself. We can't do enough justice to each one of these topics in a course, like in a one semester course like this. So how do we plan to deal with each one of them? Whether it is as far as the FRPs are concerned, or fiber reinforced composites in general are concerned, we will combine them along with the fundamentals. We will not study it as a separate subject. We will combine it along with the fundamentals, because when you're dealing with the fundamentals, we have to deal with materials. We might as well deal with composite materials and deal with metals as a separate case, where isotropy is a special case of anisotropy. So that is essentially what we are trying to do, which means that right up front we will take up the constitutive, the composite material constituents, whether it's the fiber, the matrix, there are certain additives which could be added, and depending on the manufacturing process, especially if it's hand layup, etc., there could be certain voids that are of concern. How that voids are distributed, of course, usually it is random. So how that kind of affects, etc. So the composite materials constituents, primarily fiber and matrix, each of their individual material properties and how they give rise to the overall material property of their composite, what we call as the micromechanics of composites. So that's essentially what we will touch upon, and there are very state-of-the-art complex models for micromechanics. We'll not go into it. Rajesh, for example, his PhD work is related to understanding micromechanics in a better fashion. So what we are trying to do here is to use those simplified what are called as rule of mixtures kind of methods in order to, from the properties of fiber and matrix, get the property of the composite overall for each layer, and then build up for the laminate, and then for the overall structure, be it a plate or a beam or a shell. So then we get the constitutive law of the non-homogeneous anisotropic solid structures that you have to start with as 3D, and then a dimensionally reduced model where if it's a shell we go for 2D, if it's a beam we go for 1D. So how that overall process happens, we will blend it into the study of the fundamentals, and it's not so difficult at all, because it's just a question of your still being in your three-dimensional space, which is very easy to imagine. What you are doing in a one-dimensional space, when we first study strength of materials, we talk of Hooke's law. You are applying a stress in a single direction, there is a strain in the same direction, they are related to each other by the Young's modulus. So that's how you bring about the Young's modulus concept. So it's essentially a one-dimensional model that we have. The same thing we are generalizing, and we are at a level where it's very easy to imagine that three-dimensional generalization. And in fact, even that will not be eventually required, because most of these are made out of plies, which are essentially 2D, and then later on these stiffening structures are all 1D, so you even bring down back to the 2D or 1D model. So is there a need? Anyway, you're going to go to a 2D or 1D, why should you go for 3D? That could be a fair enough question. But if we directly jump to 1D, as most people in the initial history of mechanics have done, you tend to make a lot of assumptions, approximations, sometimes valid, sometimes not valid, essentially what we call as ad hoc approximations, which are valid for particular situations, but may or may not be valid in a general situation, in a more general situation. So that is what we want to do away with, and see that how to move from 3D to 1D in a more rigorous way, which is physics-based, which is also utilizing some of the state-of-the-art mathematics in order to do that, so that what you end up with is almost as good as what you started off with. But at the same time, you have already got an understanding of 3D elasticity, at least the basics of it, and then you have seen how the dimensionally reduced models also work. So the constitutive law of non-homogeneous anisotropic solids and laminates is what would be a fallout of that. So that's how we will be looking at the first F, additional F. The second additional F that we had was what we are talking about is failure, flutter, etc., the buckling and other instabilities. For this, again, this again is a topic by itself. A lot of research going on into it, especially the geometric nonlinearities that are involved, because as I said, the displacements and rotations are very large. Even though it is still an elastic regime, that is, the strains are small, you have large displacement and rotation, which makes this a geometrically nonlinear problem. In other words, your strain displacement relationships are nonlinear. In other words, epsilon xx, the strain in the longitudinal direction x direction, which you typically define as dou u by dou x, which is essentially the displacement u in the x direction differentiated with respect to the coordinate measure along the length, which is x. That is a linear model. So you have to go for the additional terms there, make it a nonlinear model. So unless and until you do that, you will not get accurate results. So that's essentially what we are talking about here in terms of looking at in terms of the current state of the art. They really go into the depth of that geometrical nonlinearity. Whereas here, purely from the imperfections point of view or the misalignment in the loading, etc. So we'll take up some of those typical cases that you have done with in your strength of materials course in understanding Euler column buckling. We will try to extend that to a few other cases like sheets, because that's of primary concern to us. As I already told you, the top skin of the wing is allowed to operate in a post-buckling regime, which means that we should be not just interested in the column buckling, but in particular the plate or shell buckling, which is a thin sheet that we are talking about. Earlier days it was sheet metal that was used, so it's that terminology still remains as sheets, even though you might be making it out of composites. So then what happens beyond the buckling, how the deformation takes place, so a little bit of insight into that. And then of course, I don't know, usually we don't have time on this, depends on the pace at which I go, but I do not want to rush through anything. So in case there is time, we will probably look at, if not flutter, at least divergence to illustrate with some simple models, so that you have an understanding of what it means going from elastic instability to aeroelastic instability, where the aerodynamic forces are also involved. Essentially it's an energy transfer that is taking place between your elastic mode, your aerodynamic mode, and your inertial mode. So there is some way of this energy transfer that is taking place, and that can in turn cause certain potential instabilities. We will look at using simpler models. Then the third F that we already talked about is fracture mechanics. Now we are saying how do we deal with it. So in this slide we are repeating all those 5, the first 3 to start with, and but we are saying how we are going to handle it. I think I already mentioned this fact that we are going to use Griffith's original concept of the strain energy release rate in order to understand this, and we will calculate it for some simple composite structures actually. And we'll take benefit of the global nature of this whole thing and the relation to change of total strain energy stored before and after the crack extensions. What it essentially means is that it's kind of breaking up this word, this abbreviation, SERR, strain energy release rate. So how the strain energy is getting released because of the crack. Usually strain energy is something that is stored within the structure. It's a healthy structure, but now it is a structure that is getting damaged. There's a crack that is developing, therefore its length of the crack is increasing, and at the point where the crack is expanding, or multiple points, we are dealing with multiple cracks or different kinds of cracks that we can deal with. So essentially what is happening is that there is a change in the strain energy from a particular size of the crack to a different size of the crack, and how, as the crack size increases, how the strain energy is getting released. Because one way is the strain energy that is stored in the material points. The other way is when some damage is occurring, there is certain release. In fact, I think I touched upon this when we were talking about the engine containments. We said we use Kevlar over there, Kevlar composites, and one of the good things about it, why it absorbs so much of energy, is not only it deforms so much, but also it gets damaged, and the damage takes in a lot of that energy. So that's the reason. And same thing even in your cars, the earlier here, right? Oops, that's okay. Anyway, I'm done with that. So we'll. I think it's time for 1.5 hours. That's good. So what I was talking about is, yes, the Kevlar composite, the way it absorbs that impact energy is partly through deformation and partly through damage. So, and same thing in the cars. In the let's say the early 1910, 20 that period, they were building the front portion of the car with very rigid structures. The whole idea is they thought it's so rigid that it will be safe for the people. But that rigid kind of design, what it did is it transferred all of the energy of the impact when there is an accident to the passengers. So the fatalities and all damages to the passengers and driver were much, much more then compared to now, when we have a flexible structure up front, so that kind of damages itself in order to, it's kind of a self-sacrifice that it does in order not to transfer all of the energy to the interiors and the occupants. So that's a similar concept we use for the engine containment as well, and all of those we can better understand if we had those Griffith criterion, strain energy release rate, etc. Okay, thank you. So we're done with the class. Any of you have doubts or questions, you can ask.